Thank you. So this is a joint work with my postdoc Mingqiang and my student Chuan. So we are going to present a system called the CDStore. Here we consider a scenario where we want to outsource data storage to multiple cloud storage using the multiple cloud storage model. So in this model, users will store the data on different clouds, and these clouds will be operated by independent cloud storage providers, and they could be abstracted into an aggregated storage pool. Actually, we use diversity of the multiple cloud storage to achieve two main properties. One is the reliability or fault tolerance. We have seen many cases that the cloud is not always reliable, and we have seen many cases that a cloud may experience outage for hours or even days. If we use the multiple cloud storage, we can distribute the data with redundancy across multiple clouds. So if a cloud fails, we can still reconstruct the original data from other working cloud providers. Another property is about the it avoids the vendor lock-in. It has been shown that if we use the multiple cloud storage model, if we want to switch from one cloud provider to another cloud provider, we can reduce the size of data transfer during the switching. Another property of multiple cloud storage is the security. In this case, the attacker will need to compromise a sufficient number of clouds in order to get access to the data. This will increase the difficulty of the attack because right now the attackers can need more resources in order to get the data. So to realize these two properties, reliability and security, one approach is secret sharing. So the idea is you have a piece of data input that you want to protect, which we call the secret. It will transform into multiple pieces, which we call the shares, using the secret sharing algorithms. And these shares will be distributed to different clouds. And secret sharing can achieve reliability because the secret could be recovered from enough number of shares. In other words, if some shares are not reliable, are not available, we can still recover the original secrets from other shares. Also, the secret cannot be accessed if we don't have enough shares. So the attackers need to compromise enough shares in order to reconstruct the original secret. So the secret sharing can achieve both reliability and security. And there are many ways to implement secret sharing. The classical one is the Shamir scheme. Another one is the RAM scheme, which is a hybrid of Shamir scheme and also the Rabin's information dispersal. And a more recent approach is the all or nothing RS implementation. In general, secret sharing has much higher redundancy overhead compared to erasure coding, which gives reliability without security. But recent approach, the all or nothing RS approach, shows that we can reduce the redundancy of secret sharing to slightly higher than that of erasure coding, while we can still maintain the security in the computational sense. So we believe that secret sharing still has its benefit, will have its practical value. Nevertheless, we argue that secret sharing still has high storage overhead because it prohibits deduplication. Deduplication is a technology that is well used for removing the content redundancy. So the basic idea is if you identify two identical data copies with the same content, then you only need to store one single copy, while having another copy referenced by smaller size pointers. So in this case, we can reduce the storage overhead. However, for secret sharing, its security builds on the embedded randomness. So it embeds the random input so as to generate the shares. So if we have identical shares, they will result in different shares. So these shares cannot be deduplicated. And this will lead to high bandwidth and storage overhead. Actually, the same problem is also found in traditional key-based encryption. So if you encrypt the same data with different keys, maybe owned by different users, you will have different outputs, which you can't deduplicate that. So our previous hot storage paper proposed a paradigm called the Convergent Dispersion, whose core idea is to augment secret sharing with the deduplication capability. So the idea is simple. Actually, it replaces the random input to the secret sharing algorithm with a deterministic cryptographic hash that is derived from the original secret. So the idea is very similar to the convergent encryption, but we apply this idea in the context of secret sharing. And then actually our paper also show how we integrate this convergent dispersal into different secret sharing algorithms. Now, we already proposed a paradigm, but the remaining question is how to integrate this into a real system. So here come our contributions. We propose a system called the CDStore, which is a unified multi-cloud storage system that has three main properties: reliability, security, and cost efficiency. Although this system is proposed for multiple cloud storage, I'd like to point out that this is also applicable for distributed storage systems. And in the CDStore, we propose a new construction called for this convergent dispersal, which we show has high performance or high throughput than our prior constructions. And we apply this convergent dispersal with deduplication using a technique called the two-stage duplication, which we show can achieve the bandwidth and storage savings, and in the meantime is secure, which I will elaborate in a moment. And we prototype the system, and we conduct extensive trace-driven experiments and as well as cost analysis. So let's first take a look at CDStore architecture. Basically, it's a client-server model. So a CDStore client is installed in each user's machine. This CDStore client will read the user data from the user's machine and upload it to multiple CDStore servers. And each CDStore server is hosted on a VM co-located with the cloud. We assume that this CDStore is designed for the organizations that has a large group of users who wants to outsource the data storage to the cloud. And we assume the type of workload is backup and archival, which we know have high content redundancy, which will be a good fit for the deduplication. So this CDStore system will try to achieve three design goals, which I will elaborate here. The first one is reliability. Certainly, we want to make sure that our data is available, even some clouds fail. And we can still make sure that we can access the data from other operational clouds. And in addition to data availability, we want to make sure that even if the CDStore clients fail, there will be no metadata loss. And what we do here is we offload the metadata management to the CDStore servers, which we believe are more reliable than the CDStore clients, which are typically deployed on commodity hardware. Another goal is security. Here we aim for two main security goals. One is the confidentiality, which we want to ensure that the data is kept secret from unauthorized parties, including the cloud providers. And at the same time, we want to achieve integrity, which we want to make sure that the data remains uncorrupted. When we deploy, when we integrate this convergent dispersion with deduplication, we also want to make sure that this is robust against the side channel attack, which I will elaborate in a few slides. And finally, we want to achieve cost efficiency. First, we want to use deduplication to reduce the storage cost to significantly reduce the storage space. And at the same time, we want to introduce low overhead for the VM computations and metadata management, because this overhead will be translated to the VM usage cost. We make several assumptions in our design, which we plan to address in future work. In terms of reliability, in this work, we don't consider how to improve the repair performance. So basically, what we assume here is if one cloud is unavailable, we just simply access the data from other clouds. We reconstruct the data following, for example, the classical Reed-Solomon coding scheme. There are many ways to improve the repair performance. For example, in information theory, people come up with many erasure coding constructions to reduce the amount of repair traffic. but we don't consider these issues in this work. Another one is security. We make assumptions that we assume that each secret is drawn from a large message space. What that means is we cannot predict the content of a secret. So that will make the brute force dictionary attack infeasible. Basically, this is the fundamental assumptions of any deterministic algorithm scheme where the key is a direct function of the message itself. Now, there are ways to address this issue. For example, previous work in Security Conference by Belair, they propose a key generation scheme. Basically, the idea is to generate the key using a key server and try to decouple the mapping between the keys as well as the message content. So the mapping right now will be maintained by the key server instead of deriving it directly from the message. But maintaining a key server will introduce a single point of failure, and also the key generation overhead will be significant. But in any case, this will be a future work that we consider. Another thing is when we focus on security, we mainly target the data storage. And for the communications, we require that the client-server communications be encrypted as well as authenticated. For cost efficiency, we assume that there's no billing between the communications of the collocating VMs and storage, which is true for today's cloud storage providers. So let's go into the details of this convergent dispersal, how we construct this scheme, which we call the convergent or nothing RS. So basically, this is an extension of this original or nothing RS. And we make a slight changes to this is original design of all or nothing RS is based on the rifest implementation. The idea is to encrypt small words, split the secrets into small words, and encrypt the small words independently, and then aggregate them together. Right now, we use another all or nothing transform. Basically, it's called the optimal asymmetric encryption padding, OAEP, or nothing transform. So the idea is it uses a single encryption on a large constant value block. And in our previous hot storage paper, we also consider other instantiations on top of the RAM scheme and the rifest all or nothing scheme. So the basic idea is you look at the secret sharing algorithm, and then you replace the random input with a deterministic hash. So in this case, here we identified a part where we can replace the random key with the secret hash so that we ensure that the same secret will be transformed into same shares. So let me give you more details how we how this convergent or nothing RS works. So the first step is to generate a CAONT package YT. So the Y is the head, T is the tail. So how do we generate this? Basically is to follow the several operations. The first one is, given a secret, we hash it into a small value h, and then we pass this h into a generator function, and then mask it with the secret using the exclusive OR operations to generate the y, the head y. So how do we implement this hash function and generator function? Basically, the hash function could be using the SHA-256. It could be sorted, okay? And the generator function could be the encryption functions on a large size value block C, okay? Here we use the AES-256. And then after we generate the head Y, we also take a hash and then exclusive OR with the original hash of the secret H to form the T. So we have the Y and T, and then we form this CAONT package. And the next step is we encode this package with the classical coding. Here we use the Reed-Solomon codes. So the idea is determined by two parameters n, k. So in this example, k is equal to 3, n is equal to 4. So what we do is we first divide this package into k shares, and then use the Reed-Solomon coding to transform it into n shares, such that any k of n shares can reconstruct the original package and hence the secret. Now, we now want to apply this convergent dispersal scheme with the deduplication. So the question is, how do we apply the deduplication? Well, first thing is we assume that the deduplication operates at the secret level. So what that means is if you have two secrets with the same content, then the shares will also be the same, and they could be deduplicated. And one important thing is we need to make sure that the same share will go to the same cloud. So if two users have the same secret, their shares should go to the same location so that the shares could be deduplicated. And what we do here is we number the clouds from 0 to n-1. And when we generate n shares, we basically store share I on cloud I. Here we assume that the number of clouds is fairly small, so we simply distribute all the shares to all the clouds. Now the next question is, how do we do the deduplication? And a simple approach is we just simply apply the client-side global deduplication. So what that means is on the client side, it will check if the same share has been stored or not, and then we will just upload the unique shares. But this is vulnerable to the side channel attack. What that means is the attackers and malicious users can infer if another user have stored the same cloud. So what it can do is it will try to guess the data that has been uploaded by the other users and then see if it can upload or not. If it cannot upload, if it doesn't need to upload, that means that the same copy has already existed. So what we do here is we adopt another approach called the two-stage deduplication. We try to decompose deduplication into two stages. The first one is client-side intra-user deduplication. So each CDStore client will upload the unique shares of the same user. It will just perform the deduplication on its own data. And we believe that this is effective for backup workloads because the same user will make repeated backups, make small changes to the data. And then on the server side, it will perform the deduplications on the shares from different users. So if many users share the similar data, such as for the VM images, for example, the system data, they are all similar for different VMs, then in this case, we believe that is also reduce a lot of storage space. And we also maintain the fingerprint index on the CDStore servers for more reliable management. So we prototype the system on Linux, and there are several features we try to maintain good performance. So one thing is we assume fine-grained content-defined chunking. So the chunk boundaries are based on the content, and it's based on the wrapping fingerprinting, and we pick a small secret size, which is 8 kilobytes for effective deduplications. Another thing is we leverage multifronting to speed up the encoding and I/O operations. And because the secret size is very small, so it's not good to do it on secret, upload secret by secret. It would be important to batch the secrets or the shares together to save the network and storage I/Os. Something we didn't address in our implementations is we didn't consider garbage collection and compression to further save storage space. We didn't consider multiple CDStore servers per cloud. And because we consider backup or archival workloads, so we assume that's infrequent updates, so we didn't address the issue of consistency because of these concurrent updates, but we post them as future work. So let's take, so these are our experiments. We consider different testbeds and also different data sets. So we consider the local machines where we can evaluate the computational overhead, and the LAN basically comprises multiple machines connected with 1 gigabit switch. And we also consider multiple cloud platform, which we use Google, Azure, AWS, and REST-based. For the data set, we use the synthetic, unique, and fully duplicate data to give us some baseline result. For the FSL data set, it's a weekly file system snapshot collected by Stony Brook. And we also collected our own 156 VM images in a programming course by students. So we take VM image snapshots and try to collect the data and perform the experiments. So the first result is on the encoding speed. The x-axis is the different n value n, and y-axis is the speed. If we look at the blue curve and the green curve, the blue curve is the original or nothing RS. The green curve is the convergent one because we introduced one extra hash function, so the throughput is less. Now the red one is what we propose in this work. We surprisingly find that it's even outperformed these original or nothing RS. It's mainly because we use the OAEP all or nothing transform, so we use one large encryption instead of small encryption on small words. Now, in any case, we can achieve 183 megabyte per second on local i5 testbed. And we also observe that this encoding speed slightly decreases with n, mainly because the RS coding has more overhead compared to all or nothing transform. And here we use multifronting, and we show that multifronting can boost the speed, and you can refer details to the paper. Another one is about the storage saving. So the x-axis is the different week of storage, and y-axis is the saving. So intra-user dedupe basically is the amount of saving that we can save compared to the original amount of data. We see that it's almost achieved 100% because we don't see that much change on the per user data. And inter-user dedupe is the additional saving after we do the intra-user dedupe. We find that for the VM dataset, we also achieve some sort of saving. And we believe that the reason is because students make similar changes to their VM, so that's why we see some savings. In any case, we also see some 11 to 47% of the saving for inter-user dedupe after the first week. Another one is the transfer speed. We look at different testbed and also different data set. Basically, the idea is we consider single client here, and for the unique data is 77 megabyte per second, which is network bound. Basically, the raw throughput is 110 megabyte per second, but if we consider redundancy here, that's the value that you can achieve the most. And for the duplicate data, basically it's bound by the encoding, also the chunking, which is around 150 megabyte per second. And the performance in the cloud is mainly bound by the internet bandwidth. We also consider multiple clients, and it will increase with the number of clients for the upload speed, and the details are in the paper. And finally is the cost analysis. We consider different cases of different weeks of backups and also different deduplication ratio, and we compare with two baseline schemes, the single cloud and the multiple clouds with all or nothing RS. Both of them don't have deduplication. And we find that actually we can achieve 70% of savings because we right now allow deduplications. And we see some jack curves here, mainly because we try to switch to the cheapest VM instance that can hold the metadata. So if we store more data, you have more metadata, so we need to switch another VM. But in any case, we can achieve high amount of savings. So to conclude, we propose a CDStore system that tries to unify three goals: reliability, security, and cost efficiency. There are two main building blocks here. One is the Convergent Dispersion, another one is the two-stage deduplication, and you can get the source code from this link. Thank you, and I appreciate your comments and questions.
Any questions? Okay, I have a question. So the three goals that you mentioned are reliability, security, and cost efficiency. Why isn't consistency one of the goals? And where all are you not consistent?
Because right now we assume the backups when we consider the consistency is usually when you have updates concurrently. So it's not that we can't consider consistency, just that it may not fit the right workload. That's why we don't consider here. And also, it's more complicated to the design. So, but again, it could be a future work.
I see. But for a single client, if you don't have concurrent updates from a single client point of view, it's always consistent.
Yes.
Is that true?
Yeah. Yeah.
Okay.
Yeah.
Any more questions?
It's not on. Oh, there you go. Thank you. Just want to make sure I understand it. It sounds like in your deduplication graph, I want to make sure I understood what was intra and what was inter. It looked like the smaller data set, the user's own data, if you restrict out in your model, allowing the sideband attacks by giving a separate key to each individual user, that you're getting most of the deduplication benefit even within that user's own data set. And when you include additional data sets, you're not getting a lot of additional benefit. Most of the deduplication benefit happens within a user's space.
Yeah.
It seems counterintuitive to me. Is that correct?
Yeah, for some workload, for intra-user dedup, it already achieves the most benefits. So that's why you will see here that for intra-user dedup, you can achieve almost 98% of the saving. But inter-user dedup will be effective for some cases. For example, you have the VMs where all the VMs make the patches. So each VM will make the same patch, so they make the same changes. So in this case, you will want to dedupe these changes as well. And in our data set, in this case, users make the same changes. So that's why we will see inter-user also achieve some benefits in addition to the intra-user dedup.
Okay, and can you explain this percentage savings is calculated how?
So for the intra-user dedup is the saving over the original amount of data. So
you're saving almost 100, I mean, this shows you're eliminating almost all of the data. Is that accurate?
Right. So for the same user, So let's say I have 1 gig VM image,
Yes.
and I upload 100 megabytes. So the saving will be 1 minus 100 megabyte divided by 1 gigabyte. Now on this 1 megabyte, okay, there could be multiple users upload the same 1 megabyte. So we try to find the saving among these sum of 1 megabyte. Yeah.
Got it. Okay.
Thanks.
Okay, let's thank the speaker once again.
Thank you.